All right, let's dive into one of the most common and, frankly, one of the most frustrating challenges you'll face in machine learning: overfitting.
You ever have that moment? You've built a model, you're training it, and the numbers look incredible. You're getting fantastic accuracy, and you're thinking, yes, I've totally cracked it.
But then, the moment of truth, you unleash it on new data, stuff it's never seen before, and it just completely bombs. The performance just nosedives. Sound familiar? I thought so.
Well, that whole frustrating experience, that whole roller coaster, it's got a name. It's called overfitting. And trust me, understanding it is absolutely critical if you want to build models that actually work out in the real world.
So, what's really going on here? At its core, it all comes down to a battle between two big ideas: memorization versus generalization. Okay, so here's the textbook definition. Overfitting is what happens when your model learns the training data too well. It doesn't just learn the important underlying patterns, the signal, it also starts learning every little random detail, all the noise and the weird outliers that just happen to be in your specific training set.
And here's the simplest way to think about it. Your model stops being a student and starts being a memorizer. Instead of truly understanding the concepts, it just crams for the test by memorizing the answers to the practice questions. And you know what happens next? That's a recipe for disaster.
So if an overfitted model had a report card, it would look kind of weird. It gets an A+ on all the homework, the training data, excellent performance, super low error. But then on the final exam, the new data, it gets a big fat F. The error rate goes through the roof, and its real-world reliability, pretty much zero.
To really nail this down, let's use a simple analogy that I think we can all relate to: studying for a big exam.
So think about it like this. The training data, that's your stack of old exam papers. The test data, that's the real exam. Overfitting is like that student who just memorizes the exact answer to every single question on those old papers. Generalization, on the other hand, is the student who actually takes the time to understand the concepts. Now, who do you think is going to do better when the final exam has all new questions? It's a no-brainer. Now, if you want to get a bit more technical, we can talk about this using two concepts: bias and variance. Bias is the error you get from a model that's too simple. An overfitted model actually has low bias because, hey, it's not making simple assumptions. It's fitting the training data perfectly. But it has super high variance. That's the error you get from a model that's way too sensitive to the training data. It's reacting to everything, the signal and the noise.
Okay, so we get what it is, we know it's bad, but how do we actually catch this thing in the act? And more importantly, what can we do about it?
Well, the good news is there's a classic telltale sign that pretty much gives overfitting away every single time. Here's what you're looking for. You need to watch your model's performance on two different data sets: the training data and a separate validation set. For a while, everything will look great. The loss or error on both sets will go down. But then, you'll see it. The training loss keeps on dropping, but the validation loss bottoms out and starts to creep back up. That fork in the road right there? That's the alarm bell. Your model has officially stopped generalizing and started memorizing. So once you've spotted it, what's in your toolkit? Well, you've got some really powerful techniques. You can get more data, which helps your model see a wider variety of examples. You can try a simpler model architecture. You can use data augmentation, early stopping, or a big one, you can add regularization to penalize complexity. Let's take a closer look at that. Regularization is a super clever way to fight this. Basically, it adds a penalty to your model for being too complex. Think of it like a complexity tax. This makes it more expensive for the model to create those really wild, intricate patterns that only fit the noise in the training data. For neural networks, a really popular method is dropout, which just randomly turns off parts of the network during each training step. This forces the other parts to become more robust and not rely on any one connection too much. It's brilliant. At the end of the day, this is all about finding a really delicate balance, because overfitting isn't the only problem you can have. It has an evil twin: underfitting. And this table just lays it all out perfectly. On one side, you've got underfitting. That's a model that's way too simple, it has high bias, and it performs poorly everywhere on training and test data. On the other extreme, you've got our friend overfitting. The model's too complex, has high variance, and only does well on the data it memorized. And notice, for both of them, the test accuracy is poor. And that brings us right to the ultimate goal, the holy grail of model training. We are always searching for that sweet spot right in the middle.
We need a model that's complex enough to actually learn the real, meaningful patterns in our data, but simple enough that it can generalize what it's learned to new situations. I want to leave you with this final thought because it's a great way to reframe this whole problem. Don't think of overfitting as a sign of failure or a sign that your model is bad. Think of it as a sign that you have a powerful, flexible model in your hands. Your job as the developer is just to learn how to apply the right techniques to harness that power correctly so it can go out and succeed in the real world.